Okay, so this is a quick demo of my poor man's digital ruler. Um, so here I have a ALS 31313 three-dimensional hall sensor, and on the C-beam I have some of this refrigerator magnet material, and if you look at it, it is polarized in little stripes, and the stripes are, from what I can tell, they're 2 mm pull pitch on the stripes. So what's happening is there's an X sensor that's going to sense the poles moving in this direction, and then there's a Z sensor that's going to sense the magnitude of the pole. And if you put this particular sensor in mode 0, Hall mode 0, which I think is called common mode, those signals are offset by 90 degrees. So you essentially have a quadrature signal. And so I've taken that, which is going to give me it's going to give me 4 counts per pole, which is a 0.5 millimeter resolution. And then I've combined that with this thing called anaquad, which actually slices up the quadrature signal even more, and it's going to give me a slightly more resolution. So here I've got a ball screw, and I've got a dial indicator. So you can see when I move the ball screw on the sensor down here, we get a different reading. So that goes from 352, and if I go back down to 0, it goes to 348. And if I move it really quick, we get back down to 348 in the range. So it's about it's about 1/4 millimeter resolution, and it actually repeats pretty good. So 348 right there. And so I can wind the thing all the way up to 10 millimeters. Or 10 centimeters, or 1 centimeter, excuse me. I just came off my ball screw there. But you can see it updating. So that's my little experiment. I also have this this very high resolution strip, and you can kind of barely, I don't know if you're going to be able to see this on the video, but these are 1 millimeter pull pitch. And so if I swap out the strips for the higher resolution magnet, so now when I move it 1 millimeter, I should get 8 ticks. That's giving me 6 ticks. It must be not lined up right. So obviously the position of the strip, if it's tilted, it's going to affect the magnitude reading on the Z as well as the X reading. So let's see here. I got 342 and 334. So there's my 8. So if I go 2 millimeters, then I got 351. Go back the other way. And I got 335. Somewhere in there, 334. So I think what I guess what I don't understand is how there's an arctangent calculation where you can figure out the angles, and you have to quantize the signal. So I'm essentially getting for every pole-to-pole move, I'm getting around 800 signals, and so I have to quantize that and then pull out the noise, and then figure out the phase. And if I can figure out the phase, depending on how big of a chunk I quantize the signal to, that'll give me additional resolution. I think based on the papers I've read, you can get up to 24 bits of resolution, possible resolution. I think the ADC in this Allegro Microsystems chip is only 12 bits, so I don't know. And there's probably only 10 effective bits, so I don't know realistically how much more resolution I can actually get. But anyway, for anybody who's interested in linear position sensing, This is a fun little experiment, and I can, if you're interested, post a comment below and I can put some of the source code up on GitHub. Anyway, thanks for watching.